So in 5.1, we were really just dealing with one population, categorical data. So we had 3 conditions that we had to check when it came to looking at the probability of something occurring. We had to check if it was random, we had to check if it was normal, we had to check if it was independent. Those were the 3 things. And you essentially are doing those same 3 things for every single situation that we kind of get into. 5.2 is going to be 2 populations, and it's still going to be categorical data. Categorical data is always represented by proportions. So we're using P and P hat, and we're trying to estimate the proportion of blank. So we spend 2 separate days on 1 population and 2 population. And then for 5.3, we go in and we focus on 1 and 2 populations, but this is for quantitative data. So we're going to basically cover all of means in 1 day. Now, the reason why I do that is because we spend a lot of time in 5.1 especially kind of building up this idea of 3 conditions. And then you just kind of transfer that to 2 populations. And then you kind of transfer it to means. Really, the only thing that changes between what we do for categorical data and what we do for quantitative data is 1 condition. And it's just checked slightly differently than what it is originally. But other than that, it's the same exact procedure. We're going to be doing the same exact 4 steps where we have define your parameter, check your conditions, calculate your probability, conclude. That's literally the same exact 4 steps we do for this lesson and what we're doing for 5.3. It's just it has a different setting. So a lot of the time you'll find when I try to teach this to you, the first thing I do is I try to identify, is it 1 or 2 populations, and is it categorical or is it quantitative? Because that's really going to be the deciding factor for how do I approach the conditions, because those lead to how do I calculate mean and how do I calculate standard deviation. So just going in, we will have a little bit of review of 5.1. So if you did miss that lesson, it should make a little sense because we're going to kind of go over the 3 things. Why do we have to do this? Essentially, when you're having a difference in sample proportions or sample means, you're really looking for which is better. So there's an example on your paper that basically goes through 2 drugs that are given to 4,000 patients, and they're trying to see if it helps lower bad cholesterol. So just a little reminder, they go in and do a completely randomized experiment, which means they are just randomly assigning to one of the 2 groups. Now, whenever we go in and we do this random assignment, they didn't sort people by gender, they didn't sort people by their level of cholesterol. That would be a blocked experiment. This is just completely randomized. They didn't give one person the drug in the beginning and then give them the other in the end. That would be a matched pairs. Completely randomizes, just everyone's in one big group and they get assigned to something. And then they go in and they wanted to see the proportion of subjects in each group that end up dying or having a heart attack or suffering a serious consequence. So that is going to be what they consider, and I know it seems crazy, but that's what they consider a success, is finding someone who this happened to. Now, remember, we've talked about successes aren't always the positive outcome. They're trying to see, did this occur or did it not occur? And in this case, that's what they're looking for. Did they die, have a heart attack, or suffer something serious? So they went in and they got these 2 proportions. They got 0.263 and they got 0.224. And so with these 2 proportions, it's really like, well, what do I do now? I can clearly see that one is bigger than the other, but we have to kind of think back to the idea that we have sampling variability. That's one of the big things we talked about when we were building those sampling distributions. Not every single person collected the exact same sample every single time. And so because of that, I can't just look at these 2 proportions and be like, yeah, that's going to happen every single time. So what we do is we calculate a probability. We try to see how likely is it for this difference to occur. And we're mostly, the end goal of this is seeing Is it merely due to chance, or is it a result of the drug? And when we get to Unit 6 and Unit 7, we start to introduce those hypothesis tests, where we're really, really going in and seeing, I think this is true, I'm claiming this might happen, what is the likelihood of that occurring? This is kind of the baseline. So this is kind of giving you like, here's all the intermediate steps before we enter into a hypothesis test. If you really have a firm grasp on Unit 5, Unit 6 and Unit 7 should really be a breeze, because we're basically doing the same thing over and over and over again, which is why I told you when we started this, these FRQs are some of the highest scoring FRQs on the AP exam, because it's a procedure that we do over and over and over and over again. So you kind of get a lot of repetition. So to kind of go in, we have to build a sampling distribution, because we need some type of normal model to figure out what the probability is. So the shape, and I'm going to kind of go through the three things in the top row first, and then I'll explain the conditions. We want the shape to be approximately normal, because again, in order to use normal CDF, we have to have a normal distribution. For the center, that is the mean of the sampling distribution. That is always equal to P, which is going to be the population proportion. And typically, this is going to be given in the question. So they'll tell you, we think that the population is this. We think it's 20% that are going to have brown eyes. And so you use what they tell you. Standard deviation of the sampling distribution is the square root P 1 minus P all over N. And the two formulas in the center box and the right box are on your formula chart. You don't have to memorize them. They are there. They're labeled as one proportion, so you don't have to know them. You don't get any information on it being normal, and you don't get any information on the conditions. Those are things that you have to know how to check in order to use these things. Now, for normal, if I want to be able to say the sampling distribution is normal, I need to use large counts. And so that was when we took N times P and made sure it was bigger than 10, and N times 1 minus P and made sure it was bigger than 10. If both of those things were true, we could say that the sampling distribution is approximately normal. Now, for the mean, if I wanted to be able to calculate the mean based on the population proportion, I had to go in and make sure we have random selection if we are sampling, or you have to have random assignment if you're doing an experiment. Some form of randomness in your data collection, somehow, some way. One other alternative is it could be something where you have a random event. If you are randomly rolling a die or spinning a spinner, or in our example where Egan is randomly guessing on his AP Stats final, as long as you have some form of randomness where it's just by chance alone, you can calculate the mean using this formula. Now, for the last condition for spread, this was our 10% condition, and this was where we were making sure that N, your sample size, is less than 10% of your population size. A lot of the time when we check 10% condition, we just go on and we say, this is safe to assume. Like, it's safe to assume that this is true, because we don't know how many adults there are in the population. We don't know how many teens or whatever. If they say something like, this is a large hospital or a large high school, we usually go with, it's going to pass. A lot of the time, all of your conditions are going to pass. I would say if it's an FRQ, I would expect them to pass. The only time they fail is if it's like a multiple choice question and they ask you, like, are all of these conditions good? Most likely something's going to go wrong. One thing before you all flip, you can also say it's independent. Or independent if an experiment. I mention this because there's a problem, and I don't know where, but it sticks in my head, where they're like taking scraps of fabric and they're trying to see like how fast they deteriorate. And so they're burying them. And so a lot of people try to go in and write 10% condition for that. And they find themselves saying like 10 is less than 100 scraps of fabric in the population. And you're like, are there 100 scraps of fabric? I don't know. So anytime you're really doing an experiment, it's easier to say these pieces of fabric are independent of each other. Like one deteriorating faster is not going to affect the other. So if you're doing experiment type things, you'll probably find if you try to write 10% condition, it's going to feel weird and it's not going to really make sense when you read it out loud. That's usually when you go in and say these things are independent. So just a little heads up. For combining two variables together. So the distribution is going to be very, very similar. We are still going to check the same three things. It's just we have to kind of check them slightly differently. One thing that I will kind of point out, if you're combining two or more normal distributions, you will have a combined normal distribution. So what we're going to do for shape is we're going to verify that population 1 is normal, population 2 is normal, therefore together they will be normal. When it comes to center, anytime you have an operation dealing with means, the mean is non-resistant. So if I'm subtracting these means from each other, which you will be doing because you're calculating a difference always, you're going to subtract the means from each other. So whatever proportions they give you in the question, subtract them away from each other. Now, for the spread, the standard deviation, this is one where it's a little bit different. This was always the one where I said this is like our special baby because they have so many special rules. Even when you are subtracting random variables from each other, when I go to calculate the standard deviation, you are never decreasing variability. So this was the one where you always add them together. And the other thing I'll point out is you always use the variance. So all of the standard deviations that I get, I end up squaring and I get my combined standard deviation. Now, this is just kind of giving you insight into how these rules come about. These formulas that we're going to have are on your formula chart. You really don't have to like prove how they occur, but I am going to kind of show you where they're coming from. Now, one little note, and I say this because a lot of people get questions of like, well, I didn't do it that way. How am I still going to get credit? This is really up to you. So you get to decide if I'm going to do population 1 minus population 2, or if I'm going to do population 2 minus population 1. Typically, they don't tell you what you have to do, but if in the question it says do 1 minus 2, do 1 minus 2. Otherwise, they will have two separate grading rubrics, and they will have both kind of pathways down to the final conclusion. The conclusion in the end should be the same. Even if you switch it, it should still end up giving us the same probability at the very end. You will just have a different calculated mean and a different calculated z-score. And so like your lower upper kind of changes. But it's basically going to get you the same answer. So if they don't tell you what to do, it's up to you. So we have two populations, population 1 and we have population 2. So these are going to be kind of my starting points. I sometimes swap out 1 and 2 for letters that represent like what's going on because we're going to do an example with women and men. I use W and M. You can always use 1 and 2 if that's what you prefer. It's up to you. Now, with these notations, so kind of going down the line, or maybe I'll take it step by step. We want the shape to be approximately normal. I guess I'll go down the line just so it's easier to scroll. Approximately normal. The center is going to come from, if I have one population, that's going to be equal to P1. If I have two populations, that's going to be equal to P2. So if I want the combined P1 minus P2 with my little hats, I need to be doing P1 minus P2. Now, the part in black is not the important part. That is not part of the formula. You don't have to write that out separately in order to get full credit for calculating the mean. The blue part is going to be the part that is on your formula chart. That is what we have to know we are doing if we have two populations. Now, for standard deviation, again, just to kind of show you how this is built up, they have P1 hat is the square root, P1, 1 minus P1 over N1. And then same thing for P2, 1 minus P2. And sometimes they'll have weird questions in multiple choice where they make you think you're combining it together, and then they'll be like, what's the standard deviation of men? And that's all they care about. And so then that's when I would use one of these two formulas. Now, if I wanted to combine these two things together using what we kind of just talked about, I would be taking P1 minus P2 square root, and this, I'm not going to write everything out so you don't have to, would be taking each of these standard deviations that I have and squaring them. Not what I want. I want it to go here. And hopefully from algebra, you remember if I have a squared and a square root, they cancel each other out. So the resulting standard deviation formula, the part that matters, is going in, and this is the part that is on your formula sheet, and knowing we're taking the square root P1, 1 minus P1 over N1 plus P2, 1 minus P2 over N2. So the square roots go away over the individual standard deviations because of the fact that we're dealing with a variance. But the reason why I spend a whole lot of time doing this is you have to have a calculated mean, you have to have a calculated standard deviation, no matter what. But a lot of what they're moving towards in stats is they know the calculator does everything for you. They know you can go into normal CDF and plug in the mean, plug in the standard deviation, and it's going to give you what you need. So they have those multiple choice questions where they ask you which of these would correctly calculate the standard deviation. And they'll have something that looks like this, and then all of the numbers are mixed up, or they use a different formula, or it's subtraction instead of addition. So you have to be careful to at least know that these things are on your formula chart and that they're accessible to you so that those questions where it should hopefully be easy, you're getting those easy points. So here are the three things that I want to happen. I want it to be normal. I want to have a calculated mean. I want to have a calculated standard deviation. Here's how we actually check them. So basically, all you're going to do is take each of the conditions that we just talked about for one population, and you're going to do them for both. So if I'm doing large counts, that means I'm doing N1, P1 bigger than 10, N1, 1 minus P1 bigger than 10, and then repeating that exact same condition, but for population 2. So really, nothing is changing other than the fact that you are doubling up on your conditions. So I'm doing the same thing for both groups. So I have my 4 calculations that I would check for large counts. Remember, we want to have at least 10 successes and 10 failures to ensure that we will eventually get a normal distribution over time. So it's mostly checking that your sample size is large enough, kind of according to the central limit theorem. And then we have random selection, or you can do random assignment. But the big thing that I'm going to harp on is that it has to be for both. A lot of the time, I will just go in and repeat the question. So the question will tell you, we took a random sample of blank, and that's what I write down, just to show that I verified that this condition is true. Now, for the last condition, that, again, exactly the same thing we did for one population. That's the 10% condition. And that's when we go in and check if our sample sizes are less than 10% of the population. And we do it for both. And a lot of the time you're going to go on and you're going to say that this is safe to assume, just like we did when we had one population. Usually, again, the only time that these fail is if it's a multiple choice question and you're solely being asked to look at the conditions, or sometimes it'll just be in there. But for the most part, FRQs, they're going to pass. It's never really going to be a tricky situation where they're like, oh, you should have stopped. The condition failed. You failed because you kept going. It's never that. It's keep going, check your conditions. If worst case scenario, you really truly feel like one of the conditions failed in an FRQ, I would still keep going. And then in my conclusion, write something that says like, however, the 10% condition failed. So results may not be accurate or something along those lines. But 9 times out of 10, they're all going to pass. So, or you can say it's independent for both. Just as a reminder, because I know sometimes it does seem weird to write the statement whenever you're dealing with experiment type things. And to answer the original question, if there's a difference between the two drugs, we need to know a little bit more about hypothesis testing. That's when we go in and we'll start writing a null hypothesis and an alternative, and we'll see, do we agree or do we reject what they are saying? But that is later on. That's in Unit 6. So let's do an example. Our one example for today. Now, one thing that I like to do first is I like to read the question and I like to determine, because it's not going to be something where on the AP exam or on your test we say, this is a one proportion categorical question where you know that this is what you need to be doing. So you have to kind of decide, is this one proportion, is it two, is it categorical, is it means? Now for us, we only know proportions, so it should be kind of a given. But on the test, you will know both things. So in this case, we have a recent study examined the percentage of women and men. So that immediately tells me I have two populations. And if you're like, well, how do I know that they didn't just combine the women and men in the end? You can read further and they will generally note that they took two different samples. So like if I keep going, who get less than 7 hours of sleep at night, in this study, it was found that 45% of women and 38% of men having those two separate values, again, is leading to us knowing that this is two populations. Now, the other way that I know this is categorical, one, I have percentage. Percentage is usually a good sign that you have a proportion, which means it's a categorical representation. The other thing is the data that they're giving me is 45% and 38%. Another good sign that this is a categorical question, which makes it proportions. If it was something like, how many hours of sleep do you get at night? That's a question where people would answer with a number. That would be quantitative, that would be means. So it all depends on how are they asking the question and what are people answering with. Are they answering with success? Are they answering success, fail? Or are they answering with a number? Because this is, do you get less than 7 hours of sleep or do you not? That's a success, fail option. And then they say, what is the probability a random sample of 50 women and 75 men will result in a difference of 15% or more between the two groups? So first things first, I'm going to take the 4 categories we did for 5.1, and that's basically what I'm going to use here. Parameter, conditions, probability, conclude. So the first thing we typically do is we define our parameter. So I'm going to say proportion of women who get less than 7 hours of sleep. And you don't have to use W. You don't have to use M. You could use 1 and 2. You could say A and B if you really wanted to. As long as you have defined your variables, they really, truly don't care what you use. And you could have defined men first. It doesn't make a difference as long as it is defined on your paper. Now, here is where you kind of decide, am I going to do women minus men or am I going to do men minus women? That is completely up to you. So I have two things that's kind of occurring, and I want to make it very clear, it is not always two things. This question specifically just wants a difference. They don't necessarily indicate that they want men to be higher or they want women to be higher. They just say, I need a difference of 15% or more. So that could mean either way. So I'm going to go in and say I did women minus men. And that difference could be 15% or more. It could be greater than 15%. That's one possibility for a difference of 15%. Now, this is not true for every single question. You don't have to do two of these for every single question. And I say that because most of the time you're not. I just picked this question because I knew we were going to have to do two of them. The other possibility is when I take women minus men. So the first one that I have is the probability that women are higher. But there's also, if I'm only interested in a difference, there's also the probability that men could be higher. And that would mean that I would be looking for everything less than negative 0.15. And that's because if I have a small number minus a big number, meaning the men are higher, I'm going to get negative numbers. So this question, and this question only for now, has two probabilities that we're going to calculate. It is not two probabilities for every single question. Sometimes they'll just say, if they worded it and said, what is the probability that women are higher than men by 15% or more? I would only be doing the left-hand side. That's the only one I would care about. But just with the way this is worded, that's why we're going to calculate two. So, step one, done. Now, for the conditions, I always like to go in. I like to label what I'm checking. The first thing that we usually check is random. And I mentioned this before, but you don't have to check it in the exact same order. You really don't have to do, you should, but you don't have to put all of these steps in order as long as it is on your paper. So like say you did everything and you got to the end and you're like, oh man, I was supposed to check conditions, I forgot to do it, and you write it off to the side, but they're all there. They will give you credit on the AP exam. They don't care that you checked them at the very beginning. They just want it on your paper that you verified it was true. And so as long as it is there, they will read it. So if you forget, don't be like, oh man, I don't want to erase everything. I'm just going to not do it. Write it off to the side. It will still get full credit. So I'm going to go in and I'm just going to repeat what's in the question. Random sample of 50 women and 75 men. Now remember, when I check the random condition, that allows me to calculate my mean. So I can go on to say the mean of PW minus PM hat is equal to, the women proportion is 0.45, the men proportion is 0.38, so that is a difference of 0.07. So that is going to be the mean I use for calculating my z-score. And then, next condition, we typically check it's normal. And so this is going to require three things, or four things. Success, fail for women, success, fail for men. The women ones should seem familiar because they are the exact same numbers we used in 5.1. Bigger than 10, 50.55, 27.5, bigger than 10. And then we repeat for men. So for my people who were out for 5.1, this is basically like you're learning 5.1, but double, because this is what we did, essentially. So if all four things are true, well, if the success fail for women is true and the success fail for men is true, that means you have two normal distributions. And if they're both normal, when you combine them together, they are normal. So we would go on to say the sampling distribution of, and one little note that I kind of took from A-Day, just make sure that you are consistent in what you do. If you're doing women minus men, it needs to be women minus men throughout your whole entire question. Don't flip it like halfway through and start calculating something different, because you will not get the correct answer. Is approximately normal. You do, unfortunately, have to have that statement. Otherwise, you just wrote a bunch of numbers down and you didn't tell me what they meant. So you have to have something saying the sampling distribution of this particular graph. So for 5.1, or for 5.1, it was just a single p hat, is approximately normal. For 5.2, you're going to write down your difference that you're calculating. And then the last thing we check is independence. If this were an experiment where I was just testing something and assigning to treatments, I could go in and say that the experimental units are independent. But because I sampled from the population, I can go in to say my 50 women is less than 10% of all women, and my 75 is less than all men. And these are safe to assume, because that would just mean that you need 500 men and 750 women in the world. And there are certainly that many in the world. Okay, so with that, we can calculate our standard deviation, PWPM, again, remaining consistent. And this is the third box that we had, the P1, 1 minus P1 over N. So I'm going to have 0.45, 0.55 over 50. That's the women, plus 0.38, 0.62 over 75. That is the men. And this gives me a standard deviation technically, and I'm going to say this because I do want you to think, don't think that I'm necessarily rounding this to 2 decimal places. It comes out to like 0.8995, which then rounds to 0.09. I will highly advise, and I believe the directions on your test say to round everything to 4 decimal places. You find that if you round your standard deviation to only 2, it throws off your z-score, which then throws off your answer, and you get a very rounded answer that might look slightly different than the answer that they have on their grading rubric. So this is all 3 things. And then we kind of jump back into things that we have done before. So we have calculated z-scores many a plenty times. I'm going to deal with the greater than 0.15 first. So you always want your value that you're interested in. So ours is 0.15. And then you want your mean. So I'm going to do 0.15 minus the mean that I just calculated, which is 0.07, over my standard deviation, 0.0900. And that gives me a z-score of 8889. I don't know why the board is so slow during second period. It does not do this in any other class. 0.8889. Now, because I want it to be greater than 0.15, I'm going to go in and calculate z greater than 0.8889. We do this by using normal CDF. One of the things that College Board is very picky about is using your labels. So don't forget to label it as lower, upper, and this is going to be going all the way up to infinity because it's greater than this, mean, and standard deviation. If you are working with a z-score, it is going to always be 0 and 1. Now, this is in second VARS. We've done this a couple times, but just to show you one more time, just so you know what you're doing, if I go to my calculator and I go to second and then the VARS button that's right next to clear, option number 2 is normal CDF. You don't want to use normal PDF. CDF is the one that you want. And then your calculator should open up a window that says lower, upper, mean, standard deviation, and it should already have Mean is 0 and standard deviation is 1. You don't want to change that. So I'm going to go 8, 8, 8, 9. Infinity is typically written as 1e 99, and the E is the scientific notation E, which is second comma. The comma is right above the 7. And then we're going to have 0, and we're going to have 1. And so this gives me a probability of 0.1870. So I'm going to write that down, 0.1870. Now, for the second calculation, because we do have 2 probabilities for this particular question, I'm going to take negative 0.15 minus 0.07 all over 0.0900, and this is going to give me a z-score of negative 2.4444. Now, this is not a complement, so it's not the same z-score with different signs because we have a different mean and a different standard deviation. So don't just be like, oh, well, I just need to make it negative 0.8889. Doesn't work for this problem. So this time I want z to be less than or equal to negative 2.4444. And you'll notice that they are not the same number. So that's how we truly know these are not complements. Normal CDF, lower this time is going to be negative infinity. Upper is going to be your z-score value, 4. And then mean of 0, standard deviation of 1. And this gives us a probability, a smaller probability, because we have a larger z-score, or smaller z-score, if you want to think of it that way, of 0.0073. And so because they're just interested in the probability of this difference overall, we take these 2 things and we add them together. So 0.1943. Now, here's my big disclaimer, red flag. Again, you don't always have to do 2 calculations. This is for this one particular problem where they don't have a direction specifically noted. If you read a question and it says, I want women to be higher than men by this percentage, you would only be doing one of these things. So if you have something where it tells you they want that population to be higher, then do it that way. Don't always do 2. I know this is the one that's in the notes, and that's probably what people want to do, but it's not always 2 of them. This is only 2 because it just says a difference. Now, the last thing that we did was we wrote a conclusion sentence, and that was basically repeating the question. The probability that a random sample of 50 women, and I literally try my best in the questions that I can to just rewrite it word for word. 75 men will result in a difference of 15% or more. And this is the key word and phrasing as to why we calculated 2. Getting less than 7 hours of sleep. And this is the same exact prompt we used in 5.1, so it should seem familiar. Between the 2 is approximately, and I don't care if you write it as a percentage or a proportion, but I'm going to say 19.43%. Now, just a little heads up for your test, which is next week, next Thursday. You will have 2 FRQs. So don't feel like you're going to be writing like 4 million FRQs and you're going to have to write 17,000 things down. There's 2, like there always is, and there's typically going to be 15 to ish. I think this one may be at 15 just because it's kind of our first one back. 15 multiple choice questions. So it's the same kind of format that we've been doing. For